So welcome to all. Myself Dr. Santhosh Singh, working as an associate professor in Department of Physics. Today I am going to discuss about quasi Fermi levels. So what is quasi Fermi level? So actually we are aware with the Fermi levels. So Fermi levels are naturally occurs in between the valence band and conduction band. If your material is intrinsic semiconductor, okay, so it will occurs in between the exactly at Eg/2. If your material is intrinsic semiconductor, this Fermi level EF will occur at exactly at the center of the band gap. But what is a quasi Fermi level? So before the understanding of quasi Fermi level, we should know about some fact. What is thermal equilibrium? So in thermal equilibrium, we can understand the thermal equilibrium by understanding how the levels will populate. So generally the electrons will reside in valence band, and due to some temperature effect, they will populated or try to move in conduction band, but they will not reside here permanently. They will again come back to their original state, means in their valence band. So this upward transition, rate of upward transition and rate of downward transition means again the electrons are moving towards the valence band. Each maintain the constant rate. So whatever the available electron, means the concentration of electron in conduction band and concentration of holes in valence band, concentration of electron in conduction band will remains constant. So that thing is known as thermal equilibrium. Thermal equilibrium means the material achieved their thermal equilibrium state, means whatever the density present in the conduction band will remain same, and whatever the density of carrier present in the valence band will also remain same at particular temperature. Remember this thing, at constant temperature, these carrier density will remain same in valence band and conduction bands. Okay. So rate of this upward transition and downward transition will be constant. Then only it can be maintained, means the carrier density will be constant. So this is the thermal equilibrium. But this is the only due to the effect of temperature. Means here the pumping source. Pump means the external energy required to send these electrons in conduction band in their higher energy state. So that energy source is pumping source. So if there is single pumping source are available, so there will be one Fermi levels, okay, and their position will be always fixed, depends on the nature of your material. Why I am telling? Even if we are considering only the temperature as a pumping source, and let's suppose your material is N-type semiconductor. So you know that in N-type semiconductor, your Fermi level will be near to the conduction band. This is your conduction band. So your Fermi level will be, let's see, what is this? This is EF. So your Fermi level is near to conduction band comparison to valence band, and this will maintain their position at particular temperature and particular doping level concentration. Okay. If your material is p-type semiconductor, so the position of Fermi level, you know that near to the valence band. Okay. At particular doped concentration and at particular temperature, there will be a single Fermi level available, and the corresponding energy is known as Fermi energy for any semiconductor. And, okay. And based on the character or nature of your material, either it will be intrinsic or N-type or P-type, your Fermi level position will be, you can visualize or you can suppose where will be your Fermi level. Okay. But in these cases, your pumping energy, pumping source is only temperature. Means with the effect of temperature, only the electron can move from valence band to some higher energy state, from valence band to conduction band. But what happens if your pumping source will be more than one? Let's suppose there is a temperature effect as well as some biasing effect. Actually, the quasi Fermi level will exist for some device characteristics. For device practical application, this concept will be useful. Why? Because in device, let's suppose in PN junction device, obviously there will be some temperature effect, and for taking the operation from PN junction diode or PN junction device, you have to biasing that diode, either forward bias or reverse bias. So that biasing will also provide another kind of pumping energy, pumping source. So there will be two pumping source to provide the energy to electrons so that they can move from their normal state to higher energy state. So if there are two type of pumping energy source will available, so then there will be two types of Fermi level will be available, because you can't maintain you can't calculate the stability due to only based on one pumping source. Both pumping source should be considered because both are providing the energy to the electrons. So now in that case, there will be two Fermi levels. One will be, two Fermi level will exist in that case. One will be maybe near to the conduction band and one will be maybe near to the valence band. And both have a characteristics of Fermi level. So that's why quasi Fermi level. More than one Fermi level will be exist for some semiconductor devices. Okay. Why? Because there will be availability of more than one pumping source. So the equilibrium condition will be achieved by both pumping energy source, and with that you have to show two type of Fermi energy level. Okay. So that's all the thing is written here. Quasi Fermi level are very important in optoelectronic devices. Okay. Normally PN junction diode. In optoelectronic devices, as you will see, it is the difference between the quasi Fermi level, which will determine the bandwidth of the semiconductor laser application. So let's suppose this is first Fermi level, first quasi Fermi level. This is the second quasi Fermi level. So difference between these two Fermi levels will be very, very helpful for device application, device characteristics. It will amplify the performance of optoelectronic devices or semiconductor devices. Okay. So quasi Fermi level, it refers to two Fermi level which describe the probability of occupation in conduction band and the valence band. There are two. That's why for quasi Fermi level, due to the existence of these two Fermi levels, the quasi term came. That's why the quasi words used here. So it refers to two Fermi level that describe the occupation probability of electrons in conduction band and in the valence band. One Fermi level to describe the occupation probability in the conduction band and another Fermi level to describe the occupation probability in the valence band. When the semiconductor is in quasi equilibrium, means with the both type of pumping source are available and still your system is in equilibrium, means the available number of charge carriers in conduction band and available number of charge carriers in valence band remains same, okay, constant. So such type of equilibrium is known as quasi equilibrium because there are two type of pumping source are available. See, so this is the, I already discussed, this is the case for thermal equilibrium where single Fermi energy exists, okay. Either in N-type, this Fermi level will be near to the conduction band, but in P-type, this Fermi level near to the valence band, edge energy. But what happened, this is the thermal equilibrium. Here only in this first, let's suppose this is first figure, this is second figure. So in first figure, we are considering only the effect of temperature. But once again, we are considering one biasing effect. Another kind of Fermi level will appear. Okay. So one is already present there with the help of temperature. And now another is introduced. In N-type semiconductor, it will be near to the conduction band due to the biasing. Biasing means, let's suppose this is your PN junction. So this P-type terminal will be attached to the positive terminal of battery, and if N-type of terminal will attach to negative terminal of battery. Okay, so this is a kind of biasing. This biasing is known as forward biasing. So what this biasing will do? This biasing is providing another source of energy to available charge carrier inside the crystal. Okay, so with this source of energy, a kind of Fermi level will exist here. Okay, so now two type of Fermi level, one due to the effect of temperature, one due to the effect of biasing. Okay, that's why quasi Fermi level, and they can maintain your device, your particular crystal structure or material will maintain again the equilibrium. Equilibrium means number of available carriers in conduction band and valence band will remain same even in quasi equilibrium condition or even presence of two type of external pumping energy. Okay, so these are some facts. So interestingly, in energy band diagram represent the complex situation in semiconductor outside the thermal equilibrium. Means if you are crossing over the thermal equilibrium and you are applying some another kind of, if you are putting some another kind of energy source over your semiconductor device, so kind of quasi equilibrium condition will happen. Okay, so that's the thing is written here. In thermal equilibrium, Fermi level make a statement about energy distribution of carriers or distribution of carrier in a bands. So based on that, you can write the carrier concentration. Means in N0 is, let's suppose N0 is electron concentration. So N0 will be equal to NC F of half EF minus EC upon KT. And let's suppose This P naught represent the whole concentration. So P naught can be written as NVF of 2 EV minus EF upon KT. This is the case for thermal equilibrium condition, but this equation will modify in the case of quasi equilibrium condition, and we will see how. So outside of thermal equilibrium, EF cannot be used. You can't use EF, Fermi energy. Now, because this is the condition for quasi equilibrium, there are two types of Fermi energy is available. So in that time, you have to modify these equation in this form. N is equal to Nc plus F half EFE minus EC. EC is conduction band age energy. Here see EF. This is your Fermi energy in the thermal equilibrium condition, but this EFE is again your Fermi energy in the quasi equilibrium condition. Okay, and this will be appear near to conduction band, and see here this will a new type of one second Fermi energy, and this Fermi energy will appear simultaneously with this Fermi energy, and this Fermi level will appear near to the valence band, and with the effect of these two Fermi energy, your carrier concentration will be again modified in conduction band and valence band. So now the new carrier concentration based on new Fermi levels will be N is equal to NCF of EFE minus EC upon KT, and carrier concentration of holes in valence band will be NV F half EV minus EFH, the second quasi Fermi level near to valence band upon KT. So under Maxwell-Boltzmann statistics, you know that N is less than NC and P is less than NV. So you can modify these expression like N is equal to NC exponential of EFC minus EC upon KT, and P is equal to NV exponential of EV minus EFH upon KT. So now what will be the use of these equations? So once you take the derivative and plug into some, this is your equation. Now take the derivative of this equation with respect to x. So you will get this equation. Okay. So now put these value in current density equation. So you will get this equation. JC is equal to Q mu E N multiplied by E plus Q dC dN upon dx. And this is what? This is a kind of gradient. Okay. And this gradient is important. So JC is equal to mu C mu E multiplied by N dE upon dx. Mu is nothing but mobility of electron, and similarly JH, current due to the holes, current density due to the holes is equal to mu H multiplied by P dE upon dx. So see, these gradients is important to determine the current value inside the any semiconductor devices. Okay, and in such semiconductor devices that will be very important for some technological application. So see, the current value is very important, and these current values are determined by these Fermi levels energy value EFC and EFH. These are nothing but quasi Fermi level energy values. So that's why this is the important. So gradient of quasi Fermi level is nothing but unifying the driving force for carrier to flow. Okay. So you can draw some more conclusion about this quasi Fermi levels energy value. So JE is equal to mu E multiplied by N dE upon dE, where this dE is energy value of quasi Fermi energy level. dE upon dx is equal to minus Qn multiplied by velocity of electron. So then this JE is equal to this much. This is well known expression. So once you equate the coefficient, you will get dE upon dx is equal to Q minus Q upon mu E multiplied by V. So what is this? This is a kind of gradient. This is a kind of gradient, means something will change with respect to distance. So quasi Fermi level is nothing but effective way to visualize the carrier phenomena. What will be the what type of force or what amount of force the carrier will experience inside the any semiconductor devices, and due to that how they will contribute in the current. All these things can be visualized by quasi Fermi levels. So that's why for device characteristics, quasi Fermi levels are very, very important. So what is quasi Fermi level? A two type of Fermi energy level will exist in once the two type of pumping energy or pumping energy source will be available for any semiconductor devices. And within these such circumstances, your available carrier concentration will maintain a kind of equilibrium, and such equilibrium will known as quasi-equilibrium. And in such equilibrium, two types of Fermi level will exist, and that Fermi levels will be very, very important for device characteristics in optoelectronic application. So quasi Fermi level is nothing but you can conclude as an effective way to visualize the carrier phenomena outside the thermal equilibrium condition in energy band diagram. So that's all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.